Well, greetings and salutations. Welcome to your first video lesson of the year. We're starting things off on topic 1, of course, and that topic is function transformations, part 1 of which is horizontal and vertical translations. So in this unit, we're going to be looking at how to transform graphs, and there's a variety of ways to do so. We can stretch them, we can flip them, we can rotate them. We can just change where they're located. Whenever that happens, we can say that the original function has been mapped to the new function, which might distort or change or modify or essentially transform the graph. So there's a couple definitions here, and feel free to pause if I go through them too quickly, just to give you a chance to write them down. A transformation is a change that is made to a relation that modifies its position or shape. So it could be that we move it around somehow, it could be that we kind of distort or contort how it looks. Maybe it's both. And then there's mapping, and that's one way we talk about what transformations have happened. What happened to the original points, where do they go to make the new points? That's where we relate the original points of relation to the points of the transformation in a one-to-one correspondence. So what happened to the x values? What did we do to them? What happened to the y values? What did we do to them? Again, there's a number of transformations we can look at. And to start, we're just going to look at something called a translation. Translations are where we don't do anything to the shape of the graph, just where it's located. We can move things up and down, we can move things left or right. And we have seen this previously. Once upon a time, perhaps about a year ago, you looked at graphing parabolas. So we had quadratic relations. If we were to graph the ones on the left, y equals x squared is our parent parabola, which looks just as it's drawn here. Ugh. And take a moment, graph y equals x squared plus 3, y equals x squared minus 3 as well. What color shall I use today? Sure. I'll use this color there. I'll use something closer to this color here. Again, take a moment, try to do that on your own. Make sure you can graph that. And then we'll do the same on this other side as well. We've got these 3 parabolas. And what we know about these 3 parabolas is that there hasn't been any stretch or any kind of flip or anything. Y equals x squared plus 3 is just this black parabola, but shifted up 3. So all the points just kind of went up a few, up a few, up a few. Whereas y equals x squared minus 3 is like taking that original parabola and moving everything down a few, down a few, down a few. That is a translation. And we'll see something similar when we try the other one. Oh, I've made mistakes. I made mistakes. This is a way easier way to work. So again, graph the parent function and then make sure you graph the other two as well. Ooh, key point. Don't forget to label your axes. That's always necessary. And then label your scale as well somewhere. Don't want to get that communication error. All right, I'm going to graph these other two. I will use colors that appeal to me, like this one. And, oh, I don't know. This one. Just for recall, we know that this has a vertex at -3, 0. And that's basing things on this form of a parabola, that vertex form, where P is the x of the vertex and Q is the y of the vertex. So we have that vertex at -3, 0, which is over here. And from there we can draw the rest of the points. One thing you can note while I'm doing this is I'm not just doing this in one sudden swoop of a line. That I'm just kind of using more of a sketchy line just to make sure that this curve looks like I put some effort into it. It's like that. So you don't want to just doing this like, oh, I made my parabola. It should look neat, it should look tidy. It should look almost as if you care about it. But there's that one. And then this other one. Oh shoot, what color did I use? Good to know. This one will have a vertex at +3, 0. So we're over here. Nice, smooth, gentle curve at the bottom. This whole thing just seems to flow. And of course, don't forget to label your axes and at some point, label your scale. I have a tendency to label my scale last out of everything, just so that I know it's not gonna conflict with anything. If I write it here, it's messy, that's not even 3. I just want there to be room to write my scale. So there's that. And what we note here is, again, they have the same shape, but they're in different spots. Like I could take this purple thing and move it here. It exactly covers the black. I move it here. It exactly covers the pink. So they are the exact same shaped. They just have different positions. Moving on. Instead of saying y equals x squared, we can phrase these as functions and let f of x be x squared. That is our parent function in this case. And if we were to look at what f of x plus 3 is, well, that's just taking f or x squared and replacing it with f of x. In general, what can we say about f of x plus k as compared to any graph f of x? Well, looking back here, that's these cases. When we had f of x was x squared plus 3, it meant that we took this original parent function and shifted it up 3. When we had y equals x squared minus 3, it meant that we took this parent function and shifted everything down 3. So if we have f of x plus k, well, we know if it was plus 1, we'd be shifting up 1. If it was plus 2, we'd be shifting up 2. If it was plus 3, like we saw, we'd be shifting up 3. In general, if we're talking about f of x plus k, then we can say, that the graph of y equals f of x plus k will be k units higher. If k is 1, then it's going to be 1 unit higher. If k is 2, it'll be 2 units higher. If k is 3, it'll be 3 units higher. And we can also similarly look at these transformations that happened on this side. And this is interesting. When we said plus 3, we moved 3 units to the left. But when we said minus 3, we moved 3 units to the right. And if this had only said minus 2 instead, I guess that would have been 2 units to the right, or minus 1 would have been 1 unit to the right. Which leads us to a general statement, again, pretty much tying into our knowledge of parabolas. If we take a look at the graph of y equals f of x minus h, note the minus there. It will be h units further to the right. What we'll want to be able to do with this is explain what transformation has taken place, like explain what the effects on the graph are, and then also be able to actually graph that. So we want to be able to apply these transformations, we want to be able to explain what's going on, describe them. I believe that if you can explain what transformations are happening, then all the rest falls into place incredibly easily. So we're going to explain a few. We're going to explain how to graph y equals g of x based on graph of y equals f of x. So if g of x is f of x minus 7, we see this piece in there, which is essentially this. We know that it's inside those brackets, so it must be horizontal. So it's talking about moving it left or moving it right. Okay. Well, if x minus h is 8 units further to the right, then x minus 7 must be, or f of x minus 7 must be 7 units to the right. So you can say that we're shifting the graph 7 units right. If you want to be more formal, you can say that there is a horizontal translation 7 units to the right. Because again, when we slide it around, that's a translation. Looking at this one, this is outside the brackets is plus 10. So we're looking at a case more like this. And y equals f of x plus k will be k units higher. We're going to go up by k. In this case, it's not just some general k, it's actually 10. So you can say that will shift the graph 10 units up. Or, more formally, we have a vertical translation, meaning that we're only talking about up and down, and that is 10 units up. I triple dare you to give these next ones a try. Try using the more formal language, but make sure you at least have an understanding of what that formal language means to you and what that means in your mind. Feel free to pause the video because I'm just going to go ahead with it. So you try it, you pause it, you try it, and then resume when you want to see these answers. Going into here, let's use different colors. You're right, you're right. I'll say, what colors do I want to use? I'll say that this means that there is a horizontal translation. This is a plus one, not a minus one. So we must be going left instead. And that's just as up here, with this being a plus, we ended up shifting left. And there's another piece here. That thing says that there's a vertical translation. This f of x minus 6 business. Well, if it's minus 6, we must be moving to the right. How many units? That'd be 6. And then this minus 9, chose that color. This minus 9 is a vertical translation. But it's minus 9, which means it's not up, it's down. Here we have a plus 4, so just like this plus 1 meant left, this plus 4 will mean left. And a minus 13 means we're going down 13. And this final one, that's a minus 23, which means we're moving right. And then this plus 19, vertically, we're going upward. And that's that. So if we can understand what transformations have to take place, if we can describe them, well, we can apply them to existing graphs. Like in this case, this plus 2 says we have to go left by 2 units. And this plus 3 says we have to go up 3 units. So we can take these existing points and move them around wherever they happen to have to go. So we're going to go up 2 and over 3. I will go, it's a nice light color, lighter, that's fine. So this point I will go, left 2, up 3. So left 2, and then up 3 puts me there. If I take this point here, left 2, up 3, it's there. If I take this point, go left 2, up 3, left 2, up 3, there I am. And it looks like we hit this value right in there. So from there, left 2, up 3, and that's where we are. At that point, we just need to play connect the dots. I do want a different color. I like that purple. And this should look just like the original function, but just moved around a bit. And that's that. Feel free to try the next one. Again, you can pause and then resume the video once you're ready to proceed. I would do that now. Because I'm going to describe what happens with varying shades of purple. This means I have to go right 1. This means I have to go down 2. So I've got a point here that can go right 1, down 2. I've got a point here that can go right 1, down 2. I've got a point here that can go right 1, down 2. And I've got another point here that can also go right 1 and down 2. And I can keep this going. There's a point here. You go right 1, down 2. This point here, right 1, down 2. And so on, so forth. And again, once that's all done, you just need to play connect the dots. This nice little wavy function, whatever that is. Note this ended with arrowheads, so we should have arrowheads either end. Just like in the above example, we had a solid point and arrow at the other, so solid point, arrow at the other. And that's the end. Over here we've got these things already graphed, so we have to determine an equation for g of x in terms of f of x. So what did we do to f of x to actually turn it into g of x? Well, to do that we can take this shape and examine what happened to each point, like this endpoint here turned into that endpoint there somehow. Or other points that seem similar, like this point here turning into that point there. If I'm looking at this, I see we go up 4 and to the right 2. So if we go up 4, right 2, up 4 means that there must be a plus 4 out here. And to go right 2 units means that this must be a minus 2 right there. In mapping, we're asking ourselves what happens to x and what happens to y. Our y values went up by 4. Where's a good color? We went up by 4, which means our y values had 4 added to them. Instead of this y value of -3, it became y value of 1. Instead of a y value of -1, it became a y value of +3. Instead of a y value of -2, it became a y value of +2. So corresponding points on the shape of this graph, that's what happened. Y values went up by 4. We added 4. What happened to x? We went right 2, so we added 2 to those values. So when we talk about what happens to any x, y point on this graph, we added 2 to the x's, we added 4 to the y's. One thing that's worth noting here is that this said -2. Here we have +2. It's an opposite. Yeah, what happened in the brackets is kind of opposite of what we expected to happen in one sense. But this is what we got. Whereas this +4 stayed as a +4 there. That's same. So make sure you're aware of that. But again, as long as you can describe what's happening to the graph, you can do anything else. There's a few more examples. Oh yeah, just a few. So the point 2, 4 lies on the original graph. What point lies on this graph? And we can consider describing the change in words. I'm a firm believer in that. So what change actually happened? Well, there's a couple of things. For starters, there's this. And that says that we moved right 5. Which would then mean that we add 5 to x. And then this says that we moved 1 unit down. So we have to subtract 1 from y. That means that a value of 2, that was our original x value, well, we're adding 5, it turns into 7. And this value of y, which was 4, we had to subtract 1, so that became 3. So the new point is 7, 3. Because we added 5 to x, we subtracted 1 from y. How much work do you have to actually show for this? What an excellent question. I'm glad you asked. You can show this much. This is a 1-mark question on any kind of assessment. Just can you get the new point? Boom, there it is. Huzzah. It'd be a half mark for x, half mark for y. So that's how much work you have to show. But you are very welcome to write all this down. I find it can help you sort out the information, determine what's going on, and proceed from there. Feel free to try these other ones. Again, pause, go for it, and then try it out and play the video to see what happens. I'm going to proceed. We moved 1 unit left. We moved 8 units up. We moved 1 unit left. We subtract 1 from X. 8 units up means add 8 to Y. The new point instead of -3, we have to subtract 1 from that. So we're at -4. Instead of 1, we have to add 8 to that. So we're at 9. And the mapping, all these original XY points, we did things to them. To all the X values, we subtracted 1. To all the Y values, we added 8. And final example. Bloop, blop, bleep. We're moving 7 units right and 2 units up. Whoa, slow down there. So we're adding 7 to X, adding 7 to 2 gives us 9. We're adding 2 to Y, adding 2 to 0 gives us 2. Boom, that's done. There is some practice listed at the bottom here. I would recommend trying it out, so give this stuff a go. It's pretty much the most fun you'll ever have until our next practice. But give that a go, give that a shot, give it a stab, give it a whirl, give it a try. Of course, let me know if you have any questions on anything in these notes or anything that you encounter in these practice problems. You will have a chance to do that in class, of course, but also contact me if you need assistance outside of that time. It's been a slice. I'm going to stop recording in a second. I hope you've enjoyed this first lesson, and don't forget to look forward to the next one, I guess. So, bye.